Hello everyone, welcome back to the channel. Today we're still in the topic of complex numbers, and we're going to be looking at a quite unique style of question, which is solving z to some power n is equal to r cis theta. Now in more cases than not, they don't actually give it to us in r cis theta, but that's how we want to solve it. So quite often, the book calls it, we're solving z to the power of n is equal to a. And we'll look a little bit about questions that look like that soon. I want to give the first one where it does look like r cis theta, and we'll get an idea for that. In this video, we're going to go through 3 examples. It probably will be a little bit of a longer video because there's a little bit of explaining to do in how we set up and solve these equations. So let's get into it straight away. So the first one, just a nice, easy, basic example. You'll never get asked one like this in an exam. We'll do 2 kind of exam-style questions next. This is just an easy, basic intro one to get an idea for how we set up and solve these problems. So a few things to think about. The first thing essentially is because it's z to the power of 3, according to the fundamental theorem of algebra, we are expecting to get 3 solutions. You might think of this similar to like when we were solving in year 12 and year 11 when we're solving quadratics. So even just x squared is equal to 4. We're expecting to get 2 solutions to that problem. They would be x equals 2 and minus 2. Turns out that the power actually does tell us how many solutions we expect to get. So when we're solving linear ones, such as like 2x plus 1 is equal to 5, we're only expecting to get 1 solution to that problem. There's only 1 power of x, 2 powers of x, we want 2 solutions, 3 powers we want 3, and actually n powers we want n solutions. We're trying to get 3 solutions to this problem. So, how are we going to get our 3 solutions? Well, the first idea when we're solving these problems, once we have the right-hand side in r cis theta form, is we actually want to write this slightly more generally. So if I think about the complex number 8 cis of 60, I'm going to give a very, very, very rough drawing of where this is. I'd have to get it into coordinate form to give it more exact, but the angle we're making is 60, so roughly up here, 30, 60, 90, and we're traveling at a distance of 8. So however long we need to go here to show 8, this is going to be our complex number up here, traveling a distance of 60 and a distance of 8. Now there's actually infinitely many ways to write this complex number. They're all pretty similar to each other, but if you told me to travel a distance of 60 degrees, you could also tell me to travel a distance of 420 degrees and we'd be at exactly the same spot. So actually 8 cis of 420 is the exact same complex number. Now if you haven't noticed, what I've done here is I've just added 360 degrees on. I could do a full turn of 360 degrees, just going for a joyride all the way around, and then do 60, and I'd be at the exact same complex number. As long as the distance is 8, I can add 360 onto this. I could do 2 full circles, so 720, and then plus that 60, so I could write 780 is also the same complex number, and actually infinitely many, just adding on 360. So the first thing we want to do is we want to rewrite to this complex number as solving z3 is equal to 8 cis of 60 plus any amount of 360 that suits you. So plus 360, we're going to call it k, where k is an integer. I don't know why I did that. Integer. Why does k need to be an integer? Well, let's firstly remember what an integer is. An integer is a positive or negative whole number. So 1, 2, 3, 4, 5, or negative 1, negative 2, negative 3. So we're just saying we could add any whole amount of 360. We could add 1 lot of 360, 2 lots of 360, 3 lots of 360 onto that to get the same complex number. You could also go backwards 360 and then forward 60, you get there. So this could be negative. Go backwards 360 and then add 60. Same thing. So this is a general way to write that equation out. We add 360k. Now we use de Moivre's theorem. And essentially what we're going to do is we're going to take the third root. So at this moment I took the square root, or power of half. I'm going to take the third root to get it down to z. So I can write z is equal to 8 cis of 60 plus 360k, all of that to the power of a third. Now, if you haven't already seen the video that talks about de Moivre's theorem, that might be useful. But basically, if you have a complex number raised to a power, this becomes the power of the r, but it multiplies to the angle. So this will become 8 to the power of a third, cis of this stuff times by a third. So 60 plus 360k, all of that times by a third. So if I want to write this a little bit more neat, 8 to the power of a third, you can put that in your calculator, or what number times itself 3 times becomes 8, that's going to be 2. And cis of a third of all of this stuff, or timesing all of that by a third, is going to be 20 plus 120k. I times 60 by a third and got 20, and times 360 by a third and got 120. All right. So this is my solution. As we said earlier, I was expecting to get 3 answers to that, and this is where this k becomes useful. We're going to put 3 consecutive values for k. Ideally, or the easiest way to do that would be to pick k is equal to 0, k is equal to 1, k is equal to 2. But as long as you pick 3 consecutive values for k, you will get 3 correct solutions. So when k equals 0, I put that into this equation, I get 2 cis. If k is 0, I just have 20. If k is 1, I'm going to get, still just using this equation here, I'm going to get 2 cis of, and k is 1 in this case, which is going to be 20 plus 120 times 1, so it's going to be 140. That's when k is 1, I get 120 plus 20, and when k is 2, I end up with 2 cis of 2 lots of 120. That's 240 plus my 20, 260. And remembering back how we don't like these numbers to be bigger than 180. So going backwards, this is going to be 2 cis of the remaining to get to 360, which would be negative 100. Now you may be asking, what happens if I accidentally did a third one? K equals to 3. Let's see what happens. When k equals 3, I get z is equal to 2 cis of adding 3 lots of 120, which is 360, plus my 20, that's 380. But this is actually the same. Think of it, 360 plus 20. 360 is just a full circle. That's actually the same as 2 cis of 20, which was actually our first one. So we haven't come up with a new solution here. This is actually, you just end up in a loop. You get back to the first one. If I did k equals 4, it would just be equivalent to this one. If I did k equals 5, it would be equivalent to this one. So 380 is a full circle of 360 plus 20. So it's actually just the exact same as 20. And that's the one we've already got here. So we don't need that one. In fact, these here are my 3 solutions, and we are finished. So it's quite a long process. If we're trying to solve this problem, Z3 is equal to 8 cis 60. These are my 3 solutions. The nice news is that the method is the same for every single one of these questions. There is a first initial part that we have to do early on to get it as r cis theta for some of them, but then the method stays the same the whole way down. So let's work through a slightly harder question. We'll do 2 more examples. These are more exam style questions. All right, so I want to solve z to the power of 5 is equal to p to the power of 10i, where p is a real constant. Now, we talked at the start that we wanted these to be r cis theta. Z to some power equals r cis theta. At the moment, it's not. So I need to try and convert this to r cis theta, which initially is quite confusing and hard to think about, but if we draw it, there is I don't know the word I'm looking for. They consistently, they frame them like this, so you start to get used to them. You get familiar with the way that the exams like to write these questions. And also just thinking z to the power of 5, I'm expecting to get 5 solutions. So we'll keep that in mind. All right, let's try and plot where the heck p to the power of 10i is, as long as p is real. So they're telling me, so think about it as 5 to the power of 10i, or 6 to the power of 10i, or negative 8 to the power of 10i. It's just a real number to the power of 10, and it has an I with it. First of all, power of 10, no matter if I'm positive or negative, powering 10 makes something positive. So even if you were doing negative 3 to the power of 10, it's still going to be positive. So the first thing I do when I have a question like this is I try and imagine where on earth, roughly, is p to the power of 10i. Now, the fact that it has an I with it, so let's do an example. If it was 2 to the power of 10, whatever 2 to the power of 10 is, a big, big number, it's that number I. So it would be up here somewhere. If it was 5, it would be 5 to the power of 10i. Again, it's any number I put into here, even if I put negative 1 in here to the power of 10 would make it positive, and it's I. So this number is somewhere, and it's probably a lot higher than that, but it's somewhere on this axis. And it's actually p to the power of 10 in my I axis. Great. That's all I need to be able to write this in polar form. So we're going to rewrite this, or actually let's just quickly try and think about this. If I wanted to write this as r cis theta, well, the r is usually, we use Pythagoras, but if we're on one of our lines, it's actually just the distance that I traveled to get from the origin up there. And that distance, let's remember, if I put like a 2 in here, it's just 2 to the power of 10. It's just whatever it is. So my r is actually p to the power of 10. The distance that I travel is p to the power of 10. The angle that I'm making, and examiners will always pretty much put it either on one of our 4 axes or one of my 45, 135, 225, or 315. One of those angles, cutting half my 90s and stuff. So this one, the angle is just 90 degrees. I'm going to use radians for this one just because I used degrees in the last one. So it's pi over 2. Pi being the whole way around, we're going just to here pi over 2. Half of the whole way around, pi over 2. So I'm going to rewrite this question, writing it as r cis theta. Z to the 5 is equal to r, which in my case is p to the power of 10, cis angle, which is pi over 2. But like I said, we can write this more generally with a whole circle added on. We did 360 for my last example. Because I'm in radians here, a full way round is 2 pi. So I'm going to add 2 pi k onto this. So that's kind of jumping straight to the equivalent of this part that we did in that last question. I've added 360k. I'm adding 2 pi because I'm in radians. Most textbooks and answers are using radians as opposed to degrees. I believe in the exam you're allowed to use either. We'll use radians. So P10 was my distance I traveled to get up there. 90 degrees or pi over 2 was the angle I made to get there. So I've written it in this form. And now we go through the motions. I want to take the 5th root to make this just say z to get it down to my answer. Z is what I'm going for. Remember, if we're doing x squared is equal to 4, the goal is to get it to x. It's 2 and negative 2, right? So our goal is to take the z5 and to get the solution, which is going to be z. And I need to take the 5th root. So it's p to the 10 cis of pi over 2 plus 2 pi k all to the power of 1 over 5. And using de Moivre's theorem, this essentially multiplies to powers. So in essence, I'm raising p to the power of 10 to the power of 1 over 5. I'm actually doing this. I'll write it out. So this becomes p to the power of 10 all to the power of 1 over 5 of cis of pi over 2 plus 2 pi k all times by 1/5. Remember some basic algebra here. If I've got a power raised to another power, I multiply them in this case. So this is p to the 2, 10 times by 1 over 5. And cis of, I'm multiplying a fifth of this, so it's going to be pi over 10 plus 2 pi k over 5. All right. Now we want our 5 solutions, so we're going to pick them when k is equal to 0, k is equal to 1, k is equal to 2, k is equal to 3, and k is equal to 4. 1, 2, 3, 4, 5 solutions. Here they are. Let's quickly do them. So the first one is going to be when k equals 0, I get p squared cis of pi over 10. When k equals 1, I'm getting pi over 10 plus 2 pi over 5. This actually, probably to make our life easier, could be written as 4 pi k over 10. Just doubling top and bottom. And now I'm just adding on amounts of 4 pi over 10 onto pi over 10. So this one's going to be z is equal to p squared cis of pi over 10 plus 1 lot of 4 pi over 10. So that's going to be 5 pi over 10. We can simplify these for just the speed of the video. I'm going to leave it like that. Next one, when k is equal to 2. So 2 here, I'm getting 8 pi over 10 plus pi over 10. That's going to be 9 pi over 10. We're actually just adding on 4 pi over 10 each time now, an extra amount of 4 pi over 10. So this is going to be p2 cis of adding on another 4 pi over 10. We're going to get 13 pi over 10. And my last one is going to be p squared cis of adding one more 4 pi over 10 is going to be 17 pi over 10. And we're done. It's a little bit harder to explain how we get back to the start when I add one more on, but if I added one more 4 pi over 10 on, it would be 21 pi over 10, and 20 pi over 10 is the same as 2 pi. So that would be 2 pi and 1 pi over 10, which is actually just my first one, 2 pi being a full circle. So always, these will give all the solutions. Any more are just repeated versions of a solution that you've already got. Notice the p squared didn't change at all. It's just my angle that's changing as I go up, and that's to give all of our solutions. All right, last one. Another example. I might just go through this one quite fast with a little bit less detail, more just explaining at the start how we get to that r cis theta. So another exam style question. Solve z4 is equal to negative 16 k to the power of 8. Again, where k is a real constant. Again, it's a power of 8. They'll often do even power because no matter what k you pick here, this will become positive. K to the power of 8 is becoming positive, but we're timesing it by a negative, so this is negative, and there is no I. So first of all, I need to try and visualize where on earth this is on my complex plane, and I want to write it as r cis theta. That's my goal. We want all these questions to be z to some power equals r cis theta. So no matter what k is, k to the power of 8 is positive. I'm timesing that by negative 16, so this is a negative number, and there's no I. So it's just on my real axes, so this is somewhere over here. Negative 16 k to the power of 8. My r, this is often the part that people make a mistake on. The r is not negative. Now, any complex number over here, we're just thinking about the distance, the modulus, the r is the distance I would travel from here to get to here. The fact that we're going, so the distance is just the length. The fact that I'm going this way gets catered for my angle telling me to come over to here. The distance is purely a length. My angle will tell me to come to here. My length will tell me how far to travel in that direction. So my r is always a positive number. I travel 16 k to the power of 8. My angle tells me to go the direction of 180 degrees or pi radians. So that is what my angle and my r are. So writing this out again, we get z to the power of 4 is equal to 16 k to the power of 8 cis of pi plus 2 pi k, giving it more generally. And now I want 4 solutions. I'm going to take the fourth root. I'm going to do this in one go. So this becomes 16 k to the power of 8 all to the power of 1 over 4. So the r gets the power, and the angle multiplies by the power, 2 pi k, that's multiplied by 1/4. We end up with the fourth root of 16 is just 2. 2 times 2 is 4 times 2 is 8 times 2 is 16, so it's 2. And k, I don't know why I put 18, 8 times by 1/4 is going to be 2, so that's k to the power of 2. and we have cis of pi over 4 plus 2 pi, I'll keep it as that actually, 2 pi k over 4. I won't simplify that, keep them both over 4 so it makes my life a bit easier. And now I'm doing, as always, k equals 0, k equals 1, k equals 2, k equals 3 to get my 4 solutions. My lights have just gone out, but hopefully we can still see what I'm doing here. Alright, here are my solutions, very quick. 2k squared cis of pi over 4, that's when k equals 0, I get none of that, 2 pi over 4. When k equals 1, I get 2k squared cis of adding on another 2 pi over 4. That's going to be 3 pi over 4. When k equals to 2, I've actually picked a really bad number k because it's nothing to do with this k. It's to do with this k over here, so I apologize for that. I should used C or M or something. So when I have two lots of that, that's going to be 4 pi over 4 plus pi over 4. That's going to be 5 pi over 4. We're just adding on 2 pi over 4 essentially, and my last one is going to be 2k squared cis of adding on another 2 pi over 4 is going to be 7 pi over 4, and we are finished. I'm sorry that my lights went off, hopefully you can still see that. Thanks for watching. If you've been enjoying these videos, hit the like, hit the subscribe, send it to as many people as you can. Thank you very much. We'll catch you guys later.